Okay, so good morning everyone. My name is William von Woensel. I'm here to give a presentation about the paper that I published at this conference, which is called SmartRL, Context-Sensitive Ontology-Based Rule Language for Assisted Living in Smart Environments. So, assisted living, that's the context in which this talk will take place. Among other things, it helps patients to deal with cognitive decline, like patients who have Alzheimer's. In particular, it focuses on assisting patients to perform so-called activities of daily living. And these are routines that take place every day, like doing the laundry, washing up, cooking, attending to personal hygiene, cleaning the house, and so on and so forth. And this can entail moving the patient to an assisted living home. This can entail having a caregiver drop by once or a few times a day to help them perform those tasks. Of course, being computer scientists, we go about it a different way. We focus on using smart environments with embedded smart services to help with these assistive tasks, to help them perform these ADLs. And so in this paper we focus on two kind of general assistive tasks. First of all, guiding the patient through these activities of daily living using all sorts of smart services. This can entail suggesting the next subtask to be performed. Right, when you're, for instance, cooking, you're doing cleaning, doing laundry. These are all relatively complex routines, especially only if you're, of course, cognitively declined. Even by leveraging these smart services, we can even execute certain subtasks in advance to help the patient achieve these ADLs. And secondly, in case of unusual activities such as falling down or unusual sleeping behavior and so on, we can issue alerts to caregivers or in extreme situations, even call the emergency services. So these are the two running examples in the paper, and I will also use them through the presentation. Firstly, unusual activity, we will focus on sleeping. Right? So say that you have this condition, it's at nighttime, and you're not in the bedroom, or you're being physically active, something's wrong. Right? So we want to maybe alert the patient to this, or maybe alert the caregiver. Similarly, at any time of day, and you're being inactive, and you're not in a bedroom, something's wrong too. You might have fallen asleep on a couch, which would result in your muscles getting sore and so on. So that's also a problem. And for instance, physically active, this can be detected with a smartwatch or something like that. You're genuinely not moving for a certain period of time, which means that you're asleep or something else is wrong. And so we issue alert similar to some caregiver in that case. At the same time, in a real-world setting, we don't just want to call 911 whenever the patient goes to the bathroom for a certain period of time, right, during the night. We want to make short-term allowances. We want to allow for certain conditions to take place for an extended period of time before we issue an alert. Right, for instance, we allow them for 15 or 30 minutes to go to the bathroom before we start calling all sorts of people. So a second, more complex routine is a morning routine. You go to the bathroom to wash up, you go to the kitchen to make your breakfast, for instance, cooking a whole meal, cooking bacon, making coffee and so on, and then eating that breakfast in your living room or dining room and so on. So we would proactively guide the patient through this morning routine. So like I said, we can actually automatically execute certain subtasks to help the patient do that. We can adapt ambient conditions like turning on the light, turning off the light, turning on the heating, turning on the stove, and so on, right? And here, importantly, we also focus on reverting then those effects back to their initial state. Right? Say we do all these things, we turn on the stove, right? Then if we don't do anything else after he cooks, and he has to turn off the stove, kind of defeats the point of helping them complete their routine. So we want to revert the relevant effects of the tasks back to their original state. And then secondly is to guide step by step through these ADL routines by, for instance, dynamically displaying instructions on a screen in the kitchen or whatever this routine is taking place. So it's clear that there are contextual and temporal aspects that are very important here. Contextual, as in it's at nighttime, not in bedroom, physically inactive. You need to go to the bathroom, in the kitchen, in the living room. These are all pieces of context. Temporal aspects here also, in case of these short-term allowances, right, the temporal aspect really comes into play here because we want this condition to take place for a certain period of time before we actually, this condition triggers. We also want to influence context, right, by setting these ambient conditions. So So enter SmartRL, right? So an expressive rule language for smart environments that we apply to an assisted living use case, and a lot of the constructs that you will see, well, some of the constructs are specifically meant for this assisted living use case. Well, this language actually kind of grew out of our own necessity to write down rules that are medically valid, and it makes sense in an AAL scenario. Maybe we found writing these down in a more elaborate rule language, a run-of-the-mill rule language accepted by a rule engine, always took our focus off the important medical aspects of that rule, right? Because it's so verbose, you have to write down 3 or 4 clauses before you actually say what you want it to say. So that's one major aspect. And so currently our parser actually just transforms, for the most part, just transforms these expressions we write in RuleML to a more verbose, run-of-the-mill rule language that we then feed to a rule engine. That's one major aspect. The second one is we also have a few constructs that are not available in these run-of-the-mill rule engines, like reverting task effects and like delaying these conditions that our parser then also supports. So a rule in SmartRL focuses on automating certain tasks in a smart environment. Condition there refers to high-level or low-level context. I'll elaborate on that in a little while, as well as temporal aspects. An action invokes smart services, right, like displaying instructions, raising alerts, and so on, as well as directly influencing context, which would, of course, involve invoking smart service, but we do that behind the scenes, right? It's like a syntactic sugar. And so on top of that, we have some, in our opinion, useful features in an AAL use cases like reverting task effects, creating activity routines as well, which I'll elaborate on in a little while. And so to achieve all this, to allow this expressive nature of SmartRL, we actually link it to a domain-specific ontology, a smart environment ontology, that allows us to specify in a high-level way these rules, in particular symbolic context references, and also easily vary the specificity. And I will come back to all of this later on. So this is an overview of that ontology. Very straightforward. So you have an entity that can be a device or a user currently. This is currently very straightforward. We're actually thinking about maybe plugging in a more extensive existing ontology later on, but this is what we're currently working with. So each entity has multiple contexts associated with it. This context can have, and this is not shown here, but it can have time from and until it was valid, certainty associated with it, the sensor that sensed it, and so on. Importantly here, it has a certain context value. That value indicates the type of context that we're dealing with. So is it an activity, cooking, being active, being inactive? Is it a property of a device like volume or brightness? Is it a certain area that the entity is currently inside of? Is it a certain time that is currently applicable to the entity in their time zone? Is it an ambient condition that is currently applicable to that entity, like noise, light, temperature, and so on? So a device then offers 0 or more services. Those services can be alerts, displays, and context services. And a context service can either sense a certain piece of context or actuate on a certain piece of context, like influence that context, like turn up the temperature or turn down the temperature. And then finally, this ontology is even kind of like fine-tuned for our running example in our paper, so we're probably going to plug in a more extensive ontology later on. So a user here carries a device, in this case a smartphone. So now I'll just go over the different features of SmartRL that kind of tailor it to a smart environment and AAL use case. Obviously, something that's important, first of all, in smart environment is the ability to invoke smart services. This is what such an action looks like. For example, on the screen variable, we want to invoke the service display, and we pass this as an argument. So relatively straightforward. Just to illustrate, our parser expands this to this kind of triple-based rule format. This is actually currently the one that's supported by Apache Gina, because that's actually our underlying rule engine that we're relying on. So we're kind of assuming also screen variable has been bound before, like present in a certain room or something like that. Screen offers a service is of type display, and then we simply call this service with some arguments. So for that purpose, obviously, we have to implement a service call architecture in Apache Gina. We can do that by plugging in a built-in. And so this is supported by our smart middleware. Just FYI, so this presentation is on the language itself, its syntactic properties, its syntax. Not going to elaborate on the smart middleware that actually underlies it. For instance, the services that we're currently relying on, we're kind of assuming they're web services with a WSDL description. They're semantically annotated using SolWSDL, semantic annotations for WSDL. So you're using SolWSDL to inject ontology concepts into these WSDL descriptions. That's how we know that it's, for instance, of type display and it offers certain services. So as I indicated before, in these smart environments, rules will often invoke services depending on the user's current context. This is something we found when we're trying to write down these rules, right? So this, for instance, at bedroom would indicate the user's currently in a bedroom. And inactive would say the user's currently inactive. At nighttime says the time at which the user is in is currently at nighttime. So just to illustrate, this is a little bit more verbose even than before. So this is how this expression expands to. So you can see this is already starting to become a hassle to write this all down. So that's, again, our rationale for this SmartRL rule language. These kind of symbolic context references are made possible by or linked to our underlying ontology. Right, so as you can see here, at bedroom actually indicates a type of room that the user should be in at that point in time, else the condition is invalid. You can easily vary the specificity using this ontology link, right? You could say it's at any room. I don't really care. It doesn't necessarily need to be a bedroom. Right, so this is then the relevant part of the ontology here. Then our parser also sees, well, bedroom is an area, right? So an area context. So it actually adds an extra context property here to our expanded expression, saying, well, currently we're assuming it should be inside a bedroom, not near a bedroom. We couldn't really find any scenarios where near a bedroom would be useful. If we do, we would likely need to expand this syntax. So this is with regards to restricting the user context. You would, of course, also want to restrict symbolic context of any kind of entity, right? So, and this can be references to high-level context or low-level context. So currently what we support with high-level context is term, so entity actually is currently inside of somewhere or has a current state. So that's the is part here. So for instance here, we say device is located inside the room that the user is currently in, right, this at room. So obviously you can nest these expressions. And this device should be in the on state, right. So we can also refer to low-level context. For that purpose, we kind of use this property path syntax. So here we, for instance, say the temperature in the room that the user is currently in should be above 20 degrees. And the volume of the device, and device is probably bound to some entity in a previous expression I'm not showing here, volume should be below 50. Right now, I'm not actually showing the expanded expressions here, but believe me, it's like 5, 6 parts. It's a huge hassle to write them down. Really, takes away your attention for what's important, namely writing down these scenarios. So this is again made available by our link to our underlying ontology. Our parser checks, is this temp here a subclass of ambient? And it indeed is. So in that case, our expanded expression would go and look for services that are located inside this location that supply the context that we're looking for. And then even behind the scenes, our smart middleware would invoke that service and retrieve the value, and then we can work with that. In case it's a subclass of property, in case it's a subclass of property, we instead look for services that are directly hosted by the device variable here. And then, again, behind the scenes, we invoke that service, we check its value, and then we can compare it to this 50 here. I'll say that this is not found in our ontology. Well, in our smart environment ontology, obviously, will be a predicate. We will follow the regular relation. So, for instance, here, we will reference the device that is carried by the user, and then here we see that this is a subclass of property. So here we would then go and look for a service hosted on this particular device and go through the same exercise again. obviously, this opens the door for all sorts of naming clashes that you have to be careful for. So up until now we invoked smart services, we referenced context, albeit from the user or arbitrary entities. So in many cases it's also useful to directly influence arbitrary context, right? Obviously you can do that manually by invoking the service call construct that I introduced in the beginning. Again, we found it very useful to have some syntactic sugar there, so we don't have to write down that service call all the time. Well, actually, writing down that service call would also imply that we would have to write down the entire expanded expression leading up to it. So here, this is very, very comparable to the previous expression, actually, the previous case. So here we say, in the room that the user is currently in, we want to set the temperature to 25. Here, we want to set the device volume of the device variable to 0. Right, so very similar to before, we use our ontology to resolve this to a much more expanded expression. So here we look for services inside the room that the user is currently in that are able to influence the context, or are able to set the temperature higher or lower. So, as I mentioned in that, one of the first slides about the running examples, temporal aspects really deserve special consideration in assisted ambient living and in smart environments. So this syntax actually specifies that a certain condition should hold for a certain time span before it becomes true, before it can trigger a rule. Right, so here in our first example, we want to display appropriate instructions on the screen as time passes. Right, so here we say the current activity of the user should be cooking, and what he's cooking should be breakfast. And there should be a screen in the room that he's currently in. Not necessarily the kitchen, it's possible he's confused and he's somewhere else. We want to display onset screen that we bound here to display cook baking. And then as time passes and this condition still holds, still cooking breakfast, so after 5 minutes we want to update the contents of that screen and display, okay, we're going to want to cook oatmeal now, and so on and so forth. And essentially eventually we display, well, the meal is done. Second example here is issuing alerts in case of unusual sleeping behavior. Right? So here we say current time is at nighttime, the user is not currently in the bedroom, or he's being active for longer than 30 minutes. So if this condition holds for longer than 30 minutes, then we will trigger an alert somehow. Actually, at active, yes, possibly he's tossing and turning. So yeah, this might warrant a separate rule with less stringent alerts. Secondly here, for instance, they're currently inactive for a certain period of time, like 15 minutes, and they're not in the bedroom, which means, well, there's a problem. Maybe they fell asleep. We don't want them to get sore when they wake up, so we will maybe wake them up or something like that. And finally, well, not finally yet. So these kind of AAL assistive tasks often involve adjusting a device property or influencing some context in the room the user is currently in to help them perform their ADL. Right, but afterwards, we want to revert the effects of that task, right? Because else you're kind of defeating the point. If we turn on the stove for them, but we don't turn it off after the activity is done, they have to do it. So it kind of defeats the point. So, for instance, reverting the room temperature back to its original setting. So if they're at the room, for longer than 30 seconds, we put the room temperature to 25 degrees. And this has this associated cleanup rule, so to speak. So if they're no longer in that room for longer than 1 minute, we would set the room temperature back to its initial value. For that purpose, we use this special init keyword. And of course, behind the scenes, this implies doing quite some work, because this init keyword implies that we retrieve the initial temperature before we start influencing it. This is a bit more of an extensive example. So here we revert device volume back to the original setting. So say, for instance, user cares device has an incoming call. For all devices in that room that the user is currently in, we want to set their volume to 0. Right? They're watching TV, they're listening to the radio. These are all smart services hosted on these devices. We turn off their volume, essentially. And then the associated cleanup rule is, once the call is done, of that device that is carried by the user, we revert the volumes of those devices that were bound here in this original rule, we revert them back to their initial state. Right, that's another maybe useful cleanup rule. And finally, and this is again, well, in contrast to the previous slide, this is really syntactic sugar again. So oftentimes, especially in AAL, you're specifying routines, and the different activities in those routines would often share preconditions. Well, this is kind of a way of grouping together rules that share preconditions, so you don't have to repeat all those preconditions for each atomic activity. So here, for instance, again, the user's current activity is cooking, and he's cooking breakfast, and there's a certain screen in the room that he's currently in. So this is the same example as I showed before, actually, but with this extra syntactic sugar. So we display on the screen cook bacon, and then after 5 minutes, we update the instructions. After 10 minutes, we update it, and so on and so forth. Then here, we have another kind of rule set for a complex routine called washing up. So the user's activity is woken up, and again, our smart middleware is generating these kinds of symbolic references, right, based on our ontology. So we're kind of abstracting away from the smart middleware here because that's not the focus of this talk. So we set the temperature in the bathroom constant, right, so this colon means a constant. We set it to 25. We turn on the light, and then this here has an associated cleanup rule saying if you're not in the bathroom for longer than 5 minutes, it means you're done there. Right, so we revert the temperature and the light back to their initial settings. And then after 20 minutes, right, we set the kitchen temperature to 25, and we turn on the kitchen light to allow them to cook breakfast and eat that breakfast. Right, so we're kind of assuming here that washing up in the bathroom takes 20 minutes. Right, we're lacking the services to see when they're in the kitchen. So that's about it. So conclusions of future work. We created a tailored language for rules in smart environments that kind of grew out of our need to write down rules in a very concise way to reflect certain scenarios. And we also kind of added some new concepts like delayed conditions, like cleanup rules. So it's linked to a smart environment ontology. You apply it to an AAL use case. These are some of the features that we introduced. Future work, for sure, is dealing with uncertainty in a more explicit way. Currently, we kind of work with global limits for uncertainty, so our smart middleware says, we're pretty sure this happens, so if it's above a certain value, then, yeah, sure, we'll act on it. Evaluate additional AAL scenarios, right? This language currently is really very much being pushed by our needs for writing down rules in these kinds of scenarios. So if the need for extra syntactic sugar, extra constructs arises, we will add it. And so integrated with our smart environment middleware. So we have this middleware currently, we have this language currently, and we're kind of in the process of integrating it. So like I said, our parser for by and large expands these expressions to more verbose rule language, which can be fed to a rule engine. So but the concrete integration with the smart environment middleware is still to be done. Well, that's about it. Thank you.
So, very interesting work. So I'm working in a similar kind of thing on activity recognition, and I have noticed exactly the same thing that you said, the whole hassle of writing down rules and creating them for reason. So I was wondering, SmartRL as it is probably cannot handle the case of activity recognition, but do you think that it would be possible to kind of imagine a different syntax or something that could be applied to exceptions?
No, thank you for that question. It's an interesting question. So currently we're kind of assuming that our smart environment middleware does this activity recognition for us, right? You saw like context references like active, inactive. We're kind of assuming behind the scenes this is done and this is fed to us, and now we can properly act on it. Doing activity recognition like the nitty-gritty with probabilistic or possibilistic approaches is really not inside the scope of this language. But
still, the fact that you provide constructs for
Yeah.
I mean, for the rules that I've been creating, this is enough to do the, the left-hand side of the rule. Instead of having actions on the right-hand side, you could have recognize activities or anyway. But yes,
Yes, okay, very interesting. And because it's, I see it's quite applied on a scenario, I wanted to ask, what if the people that have to be managed in the house are more than one? Do you think that those rules could be, you could implement them without risk of conflict of rules, and unwanted consequences, or maybe it should settle instead of like a more high-level of rules where you only trigger effects when maybe both people are in a certain situation?
That's a very good question. Yeah, so indeed, currently we're only assuming scenarios where there's one person in the environment because we're kind of targeting assisted living. If there's a caregiver that lives in, it kind of removes the need for this system. But no, it's a very good point that you make, and indeed, maybe at a later time we'll raise the necessity of having extra constructs in there to refer to different users. Now we only have one ampersand, and that's supposed to be the user. If there are multiple ones, yeah, we'll have to introduce extra.
It's sort of a similar question. What if the person has multiple disabilities aside from cognitive? They might have vision, might be impaired, so reading a screen might be difficult, or they might have physical limitations not getting around.
No, that's a good point too. Currently, in this system, this wouldn't involve having domain experts write different rules for that unfortunate patient. Ideally, our language would be able to pick up on that by checking the patient's profile. Oh, they're visually impaired as well, so we're using a different modality to communicate certain instructions to them. That's actually a good idea, yeah. That's,
I just was referring to the question for the last one, that it could be a couple living in the same environment, not without the caregiver.
No, that's fair enough. But even then, they would have to be like both cognitively impaired, I guess, or really raising the necessity of this. But no, at any rate, I agree that it's an idea that should be investigated.
Again, it's very interesting and wide applicability. I was wondering if the system can be also interactive in the sense that the user can have a say on the schedule, because you set a very tight schedule. I'm sure that my mother would like to be able to choose to have a shower before breakfast without you calling the ambulance. She spends too much time in the bathroom.
Oh, that's a very good point. This is very initial work. We were actually planning on deploying a UI on a mobile that would be very big buttons, big friendly letters, and allow them to not only give them instructions, but also to give feedback on those instructions. Like to say, you know what, I know I'm going to do this first and then that, and that would be taken into account by the system. That's indeed true, but this is very initial effort that we will expand on later.
You might think a speech interface would be useful too, if someone's taking a shower now.
Oh, for sure, yeah.
Is your system designed to integrate with existing systems like neutron writing systems that are existing today, and Honeywell's overall heating system?
Yeah, so our smart middleware currently kind of focuses on services that have at least an associated WSDL file with them. So web server description language that's semantically annotated. That allows us to nicely plug it into our ontology. Right, so we're assuming that each of them are semantically annotated. So we can say, oh, this provides this piece of context, so we should call it and then obtain this sort of information or influence that context. So indeed, these systems could be plugged in if we have, if we know technically how to access them, and we know what kind of information they provide or what kind of context they allow us to influence.
Okay, I think we should have a coffee break and thank the speaker again.